Two things should have popped into your announcement stream. I'm going to start with the one that probably came in first, and that is because I changed our Google Classroom to say Spring 21, you're going to need to I archive the old class in Edpuzzle, and you're going to need to enroll into our 6th period class. So you just go to edpuzzle.com and then join class, and this is our code. It is in the announcement stream. You'll need that for tomorrow, because tomorrow I have an Edpuzzle for your asynchronous learning opportunity. Right. That's numero uno. Numero dos is the calendar. We're actually going to start with the notes first and then do some reviewing with Kahoot. I had hoped to play around with a Jamboard. I'm sure a lot of other teachers are already doing it. I'm an old dog, so I'm trying to figure it out. I'm not comfortable doing it with students yet. So, and then Thursday we probably won't have time, because I want to make sure you have enough time for the quiz. So on Friday we'll do it, I promise. And yeah, so tomorrow there's going to be an Edpuzzle video by Professor Dave for you to watch on periodic trends. Thursday we'll talk a bit more about periodic trends, review, and have a quiz. And yeah, that's the plan, man. So that is our calendario. In your classwork feed, you should have gotten a copy of this document. So it's a note sheet for you. Again, you don't have to use it. Writing on paper and pencil with paper and pencil is probably better, but this will be in your stuff for the class, so you can have an easier time reviewing, hopefully. Right. I'm trying to, there we go. Figure out where you guys are. Any questions right now? All right, seeing none. Oh, there's Caius. All right, everybody's here. Good. I am going to go ahead and jump to my PowerPoint and try to go a little bit faster than I did earlier so that we have more time to review. So, section 1 and chapter 6, just kind of basic introduction to periods and families, what's in the little periodic table square, stuff you already knew. Yesterday was the family names. You have to know the family names. You can't not know them. You've got to know them for tomorrow or Thursday. So work on that. And this section talks about something called periodic trends, patterns. And we're going to get to that in just a sec. So this looks like a random black picture with white dots on it. It turns out it's an X-ray crystallography. It's an analysis of sodium chloride crystals. And sodium chloride, of course, you would commonly call table salt, is a crystalline solid. It is made of a metal and a non-metal. Sodium's a metal, okay? Oops. And chlorine is a non-metal. I gotta put my pen on here. Boop. Oh, it's gonna be green, that's fine. Okay, so sodium's a metal and chlorine is a non-metal. And it turns out they do some interesting things. But these little dots are nuclei of the sodium and chlorine ions. And this pattern, to someone who's good with three-dimensional spaces, which I am not, is showing a cubic pattern. So that a crystal is something that has a regular repeating pattern to its structure. And pretty much all solids are crystalline, even though they're not sparkly like quartz crystals like you think of a crystal. To a material scientist, crystalline just means there's a regular order to how the atoms or ions arrange. If you are able to, some of you have rock salt for like making ice cream by hand, or some of you might use it to put on your sidewalks at home to when it gets really cold and freezing, and ice to help melt the ice. Some of you have kosher salt, which tends to be coarser than the normal salt you have in your shaker. But if you have a magnifying glass, maybe you don't even need one because you probably have good eyeballs being young. If you look at those crystals closely, you'll see that they're cubic in shape. And I will show you a, if I remember, somebody help me remember, when we go back to campus, whenever that is, I'll try and remember to pull out a halite crystal that I have. Halite is a geologist name for large chunks of sodium chloride. It's a mineral. And halogens, remember, group 7A or 17 next to the noble gases, that's where chlorine lives. So halite is for mineral size sample sizes of sodium chloride. Kind of cool. All right, so periodic trends. These are patterns, right? Trends are patterns, like being trendy and wearing periodic table shirts. Fashion trends, right? Not everybody wears the same thing because they're not cool like me, but not every atom follows the trend perfectly, but there's a general relationship that you'll notice, and that's what we're going to focus on for 4 different things. The first one is atomic size. The second is ionic size. So we've got to figure out what the heck an ion is. Third one is ionization energy. So that's something to do with energy needed to ionize something. And then finally, electronegativity. And again, you know, these are all weird words you, I'm sure, haven't heard before, but you know that electrons are negative. So this probably has something to do with electrons. Okay, so quick deduction from looking at the word source. So we're going to focus on atomic size today primarily and talk about what ions are in a little more detail. There's a reason why elements in the same family behave the way they do. There's also a reason why these trends are apparent, okay? And it all boils down to atomic structure. And of course, you know that means the positive nucleus and the arrangement of the electrons outside of that nucleus. So 3 things that we're going to specifically talk about in terms of atomic structure. The first one's nuclear charge. So you should think, nucleus, that's what Rutherford found. Oh yeah, those alpha particles bounce off of it. Remember, the nucleus is positive. Why is it positive? Because the protons are positive. Yes, there's neutrons in the nucleus, of course, but they're neutral. Okay. So nuclear charge is one thing that explains these trends. Another thing is something called shielding. So you know what a shield is, right? Knights in shining armor have their shield to block things. Okay, well, shielding is what the term that's used to explain how the layers of electrons, remember our onions, okay, the layers of the electrons, they're all negative. So negatives attracted to positive, but negative repels other negatives. Okay, so these layers of electrons create literal force fields, electrostatic force field, blocking other electrons from being attracted to the positive nucleus. And then finally, the actual electron configuration. How are they stacked in those layers? The most important ones, again, I cannot emphasize this enough, the s and p orbital electrons. Remember, noble gases end with s2p6. 2 plus 6 is 8. They have an octet. What do they have? What do we call those outermost s and p orbital electrons? Those are the valence. Believe it or not. valence electrons. The goal, if you will, of an element is to get noble gas configuration. And so they're going to try to get 8 in that outermost layer. If they don't have 8, they're either going to lose or gain electrons to get to a layer that has 8. Sure, my dog is barking. So I may be nerdy, but only periodically. Atomic size. Well, you know what radius is. This gets all fluffy. How big is the atom? Well, what are we talking about? We're actually talking about the distance between the nuclei. If 2 of them are bonded together, what's the distance, right? So the radius is half the distance. Remember, I can't remember because I haven't talked to you about it, but in order for atoms to bond, their cloud spaces have to overlap. And so once they overlap them, they're bonded. That makes that inner area a little bit smaller, if you will. So like on this one, this image of the hydrogen molecule, there's 2 hydrogens stuck together. Another little note that I don't have on your follow sheet, there are 7 what we call di, and these are super important. So the sooner you start processing this, the better. Diatomic elements, and you probably know that the prefix di is the same as the prefix I. It means 2. So there are 7 elements in their pure elemental form that go around as molecules, and they're stuck to another one of themselves. So hydrogen bonds with hydrogen, nitrogen bonds with nitrogen, oxygen bonds with oxygen. So when you say hydrogen, and you have a sample of hydrogen gas, it's H2 molecules. Say nitrogen, like 80% of our atmosphere, 78%, it's N2 molecules. Oxygen, O2 molecules. Okay. And remember that subscript 2 just means instead of writing OO or HH or NN, right? In addition to these 3 very important elements, there are 4 others in the same family. You won't normally see them horizontal, but it fits better on the picture. I guess that's why they did it. Hopefully some of you recognize this family. It lives next door to the noble gases. These are the halogens. They are group 7A, which is also group 17. All of them end with S2P5. Everybody in the halogens has 7 valence electrons. They just need 1 stinking more electron to get an octet. So they're going to steal from other elements. There's a lot of chemistry on that one slide. All right, we'll keep going. This image tries to give you a relative, oh gosh, that was a really quick line, a relative size of group 1, alkaline metals, group 2, alkaline earth metals. We skip the transition metals. This is the block D is missing. We're just focusing on the representative elements. 3A is now 13, 4A is 14, 15, 16, 17, and group 18, the noble gases that are too good. Too good to interact with anybody are off over here. Okay, so just looking at those dots, you should notice a pattern going top to bottom. And you should notice a pattern going left to right. So down through a family or across a period, there's a repeating trend. Little's at the top, big's at the bottom. Big on the left, littler on the right. There's some little glitches like over here. That's why it's not, set in stone absolute. It's a pattern, it's a generality. There's always exceptions. Okay. So another way to look at this, and this is a little harder to process initially, on the y-axis is picometers for that radius distance. And then down here is atomic number. And remember, that's the number of protons. How big is the nucleus? Here's neon. This one would be calcium. 50's 10. I keep saying that, and I don't have a periodic table in front of me. Okay, and so there's something going on here. All the alkali metals are bigger than the noble gases. And as you go from alkali metal to noble gas, okay, you get small. Alkali metal to noble gas, you get small. Potassium to noble gas, you get small. There's some weird stuff going on with the d electron, the orbital electrons. Look at that in a second. But again, lithium's at the top of the family, it's the smallest. Cesium's at the bottom, it's the biggest. Helium's at the top, smallest. Xenon's at the bottom, biggest. This is kind of a fun way to look at it also. Kind of looks like a keyboard of the elements here. Notice alkali metals, hydrogen, lithium, sodium, potassium, rubidium. Biggest at the bottom. Duh! Of course the biggest is at the bottom. There's more protons, there's more electrons, there's more layers of electrons. Okay? Left to right, across a period, potassium to krypton. It's biggest on the left, it gets smaller, and then it gets a little bit bigger, but it doesn't get as big, okay? It's a general trend. Just notice one little area here, and we'll come back to this again, but 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Notice it gets smaller, and then they get bigger again. There are transition metals. So scandium, 1 in the D. Titanium, 2 in the D. Vanadium, 3. Chromium, 4. Manganese, 5. And then starting with iron, we have to double up. And so there's something going on with the D to change the size of the atom. All right, in general, atomic size decreases as you go left to right across a period. Gets smaller. Big on the left, small on the right. And in general, as you go top to bottom, you get small at the top, bigger at the bottom. This one's pretty solid. I don't think there's any exceptions on that. Okay. So that is a periodic trend in atomic size. Why is always the question. So, or maybe not for you, but for scientists, biggest on the left, smallest on the right. If you're adding more protons and electrons, how come it doesn't get bigger? It gets more massive, but the volume actually gets smaller, and that's because all of the protons get stuffed into the little tiny nucleus. Okay, the nucleus' size is pretty consistent atom to atom. They're all those protons hanging out together with neutrons. The electrons are, randomly floating around out here. This magnet, if you will, of the nucleus is getting larger as you go from left to right. All of the electrons are basically at the same energy level, but they're still scattered. Remember that video we watched, them miles away, okay? Compared to the nucleus, which is the size of my fist. So this nucleus gets more and more and more and more powerful, and the little teeny tiny electrons get snugged in tighter the bigger the nucleus gets at a particular energy level. At another energy level, that's a different story. Top to bottom, no brainer. Of course, they're bigger. Yes, there's more protons. Yes, there's more electrons, but there's more layers in our atom onion. Guess what those layers do? They shield the other electrons from the nucleus. Okay, they block the positive charge from being able to grab the negative electrons. They act like a shield, a knight's shield. All right, atoms. I'm flinging around words. You need to get them straight and how they really are used. Atoms are neutral. They have no charge. That's because the number of protons equals the number of electrons. Same number of positives, same number of negatives, no charge. Ions, on the other hand, have more or less electrons than protons. It depends on the kind of ion. So they have a charge. Ions are charged particles. They can be positively charged or they can be negatively charged. There's a pattern to that. Positive and negative ions are going to form when electrons get transferred. Now, the electrons that leave metals, remember metals are losers, they don't just vanish. They have to go somewhere. They're matter. You can't destroy it. So here's sodium. Remember, sodium has 11 protons. Doesn't matter how many neutrons, it really doesn't, but it also has 11 electrons. So a sodium atom has no charge. It doesn't stay an atom for long. Okay, you will never find sodium in its pure form. Remember its configuration: 1s2, 2s2, 2p6, 3s1. There's nothing in the 3p. That means sodium, the highest energy level, has one valence electron. All by itself, shielded from the nucleus, it's gonna get ripped off of that atom in no time. What does that do for the atom? It creates a positively charged ion. So again, still have 11 protons, but now we only have 10 electrons, net overall +1 charge. Sodium and all the members of the alkaline metals have one valence electron. All of them lose them. Why? Because if you have 1 and you need to get to 8, you would have to pick up 7 more electrons. That means you have to have a bigger nucleus. That doesn't happen. It's much easier to lose that 1, get 10 electrons. The element that always has 10 electrons is neon. That's a noble gas, S2P6. Elements gain or lose electrons to get noble gas configuration. Metals form positive ions. All right, let's look at the other side of the periodic table. Opposite sides, super reactive. Group 1 and group 17. Alkali metals, halogens, most reactive elements on the periodic table. Okay. Chlorine's element 17 has 17 protons. Doesn't matter, it really doesn't matter how many neutrons for this discussion, but there's 17 positives, 17 negatives, no charge. Think about its configuration. It's in group 17, which is 7A, which means it ends with S2P5. 2 and 5 is 7. If it grabs one more electron, where it's going to get that from, it will get an octet. So nonmetals gain electrons. We're going to steal it. One way you'll see it referred to in books. It's grabbing it from sodium. Okay? And so the sodium ends up with a +1 charge. The chloride has a -1 charge. Opposites attract. You make a compound, an ionic compound called sodium chloride. Of course, it's bigger. The nucleus can't hold it all in. It's going to be larger than what it started. We gained something. So now we've got 17 positives, 18 negatives, net -1 charge. Again, ions are going to form by atoms gaining or losing electrons. It doesn't show up very well. Make believe that T is a plus sign. Positive ions are atoms that have lost electrons. The metals lose. Negative ions are atoms that have gained electrons. remember, you're losing a negative, just like in math, that means it's positive. If you're gaining a negative, that means you're negative. They're called anions. I'm hit, I've lost an electron. Are you sure? I'm positive. Chemistry humor. Or not. Really fast. Oh, this isn't going to show up anywhere. Oh well, I picked the wrong color for this class. I apologize. So remember, these are our S block elements. S1, S2. Okay. These 6 columns are our P block elements. P1, P2, P3, P4, P5, P6, the noble gases. Okay. If you're in group 1, you have 1 valence electron. If you're in group 2, you have 2 valence electrons. If you're in group 3A or 13, you have 3 valence electrons. Carbon's family has 4 valence electrons. 2 in the S and 2 in the P's makes 4. Nitrogen's 5, oxygen's 6, halogens are 7, noble gases are 8. Okay. Everybody's goal is to get to 8. 1, 2, 3. Okay. And those all lose. Group 1 loses 1, group 2 loses 2, group 3 or 13 loses 3. +1, +2, +3 charge. That won't be on the quiz, but I'm just getting that out there, okay? And then we're going to ignore group 4 right now because they're a little confused. They're halfway in between, right? Do 1, 2, 3, 4, 5, 6, 7. Everybody wants to be 8. Oops. So if you have 1, 2, or 3, you'll lose them. If you have 5, 6, or 7, you gain. 5 + 3 is 8, 6 + 2 is 8, 7 + 1 is 8. That is a pattern with our representative elements. If you know the column they're in, you know the charge of the ion they form. Then we write them as superscripts, so Na+. Just like with math, you don't write 1x, you just write x. We don't write the 1. I don't care if you write it. It's fine by me if you choose to write it. But scientists would say you should just write plus. We want to save our pencil red. Okay. Again, the number's understood. If you bother to write the plus, it's +1. And again, if you've lost electrons, you have a positive charge. If you gain, you have a negative charge. And I think that's all I want to say right now. All right, I know there's a lot of information. Let's see if we have any questions, and then we'll hoot for a bit. Anybody with any questions?